In this unit, we're going to look at how to model systems in our frequency domain. And so that might not completely make sense at the moment, but hopefully after the next few videos, everything will be a little clearer. And so this follows chapter 2 in the textbook. There is another method to help us analyze and represent our systems, and that's something called state space, which is in chapter 3 of the textbook. Most likely we will not have time to cover that in this class, but if you're interested in that or if it's relevant to some of your work, I would encourage you to look closer at chapter 3. So coming back to chapter 2 though, it turns out that many systems of interest can be characterized, or at the very least approximated, by something called a linear time-invariant differential equation. So linear time invariant, so often you'll see this referred to as LTI equation or LTI systems. And essentially what that's saying is if we have linear input or some combination of linear inputs, we're going to have a similar linear response in our output. That's the linear part. Time invariant means that we're going to get the same output for a given input regardless of what time we send that input to the system. So we're talking about these linear time invariant systems. So what does this differential equation look like? So here it is, taken from your book. So we have some coefficients, some derivatives, some functions of time. So let me go ahead and define those functions of time. So we have in here r of t and c of t, sort of scattered throughout there. And so what these are, our r of t is our input, and the reason we call it r of t is that this is oftentimes referred to as our reference input. And so I mentioned that in an earlier video, but just to remind everybody. And then you might be able to guess, of course, our c of t is our output, and the reason we're using c is because oftentimes in control systems we'll call this our controlled variable. So if we come back up here to our equation, we can see that we have our output c of t in one side. On the other side, we have our input r of t in all of these terms. And then all of these other coefficient terms, this a sub n, this a sub n minus 1, a naught, b sub n minus 1, and b naught, are all describing our system. So these coefficients are describing our system. So as you might imagine, particularly for higher order systems, so that means that this n or this m value are higher, we have a higher derivative order, it can get a little complicated to sort of parse out what sort of separate our coefficients, which represent our system, our input or output if we're trying to solve for one thing. So ideally what we would like to do is we would like to characterize our system with distinct input, output, and system parameters. So with input, output, and our system, let's see if I can't write that well. So let's say we want to have these distinct so that we can kind of look at it quickly and not have to parse out what's what. And so one way that we can represent that graphically, as is shown in your textbook, is with just a simple block diagram. So if we have our system here, and we have our input on the left side and our output, c of t, on the right side. Of course, looking at this, it's a lot easier to say, okay, here's our input, here's our output, and here's our system in the middle. And so we could extend this idea even further and say, well, what if we had several smaller subsystems? So what if we have something like this? So we have a subsystem. And let's just copy that. Let's say we have a few subsystems in here. So something like this, and so let's say we have sort of a initial input over here on our left. That's going into subsystem 1, going into subsystem 2, into subsystem 3, and then finally we get our usable output c of t. And so basically what we're going to do in our frequency domain is we're going to be able to use such a representation, and some key terminology that we're going to come back and talk about later is something called a transfer function. And so it turns out the transfer function is sort of representing our system. So each of these blocks above, so let me just say this represents our system. So all blocks above can be represented by a transfer function. And so what that's going to do is that's going to make it a lot easier for us to say, all right, we know we have a certain transfer function. Now we can change up our input, we can switch this R of t around, and as long as we know the transfer function for the system, we can anticipate what output C of t we're going to have. And so we're going to come back and dive into this idea of a transfer function in a later video. In the next video, what we're going to do though is we're going to talk about something you've heard before in some previous classes called the Laplace transform. And what that's going to do is help us get into that frequency domain where we want to do our analysis.